And welcome back to the Turdford Show. Hey, sorry it's been quite a while since I've actually made a video, so we'll get into this and kind of see how it goes today. So anyway, today's video is going to be kind of a quick little session on Coulomb's law. Now, most of us are familiar with this idea of Coulomb's law. It's essentially we learn about opposites attract and things of that nature. Well, obviously we can take it a step further, and we can go with a little formula Charles Coulomb came up with, and that's this, that the force between any two charged particles is equal to K times charge 1 times charge 2 over R squared. Now, you may be looking at this and going, Mr. Cole, there's a little bit of difference between what you're writing and what it says in my book. Probably the only difference between what I've written and what's in your book is there's probably absolute value bars around these charges. And the reason behind that is the only thing, so we know that there are positive charges and we know that there are negatively charged particles. But all that does is it tells us basically, well, it goes into electric fields, it tells us more. But for right now, let's not talk about electric fields. Let's just talk about right now. It just tells us that two things are attracting each other. Or likewise, let's say we had two negatively charged objects, we would know that the force between those is repelling. So quantitatively, it really doesn't tell us anything about the pluses and the minuses. So when we do our calculations, we're going to ignore those. And I'm so lazy, I may not write those little bars. So anyway, now that we've addressed some simple housekeeping, so we can look at something as simple as what about explaining, let's look at a hydrogen atom. So if we were to look at a hydrogen atom, we would have in the center, we would have a proton. So we'd have our positive proton in the center. And then somewhere out here around it, we can have our small negatively charged electron. And I think on average, in terms of an atom like hydrogen, I think this distance of separation is something on the neighborhood of 5.3 times 10 to the negative 11 meters. So not a very large gap here. And again, it is an hydrogen atom. So there's your separation. So what we could actually do then, we could try and calculate what the force, this electrostatic force, is between these two particles. And here, and I'll put a little Fe for electrostatic force. So if I want to calculate that, all I need to do is the electric static force would be equal to K. And we haven't even addressed what K is yet, but K is actually, that's actually Coulomb's constant, 8.99 times 10 to the 9. The unit is super jinky, newtons meters square per Coulomb square. So anyway, so there is our unit for Coulomb's constant. Okay, so now what we can do, we know our constant K, and so if we want to find the force between the proton, electron, and hydrogen, all we got to do is the charge of the proton times the charge of the electron divided by the radius squared, this separation between the two. So in this case, that would actually just be our 8.99 times 10 to the 9. And I'm going to be very lazy and not write my unit, so you'll have to forgive me. Well, you got to remember something. What's true about the charge of an electron and the charge of a proton? They both have a charge of 1.6 times 10 to the negative 19 coulombs. One's positive, one's negative, but in our case, remember, why am I being lazy? These are actually absolute values. So this is essentially our charge squared because they both have the same charge. So 1.6 times 10 to the negative 19 Coulomb square divided by a radius of 5.3 times 10 to the negative 11, and there I wrote my unit, good grief, I couldn't help myself, square. And technically, I really have no desire to type that in a calculator, but hey, why not? Let's see if we can actually type that in a calculator. I'm going to type it all in at once and be a little bit on the lazy side. So 8.99 10 to the 9 times what we got. 1.6 10 to the negative 19. It's always an exciting video when you watch somebody typing in a calculator. We need that term square over 5.3 10 to the negative 11. We need to square that term as well. And so we've got, look at how small that force is. Except when I typed on it, wrote on my screen, it disappeared, of course. Wow, that's not what I want. Give me back my calculator. So 8.19 times 10 to the negative 8. So 8.19 times 10 to the negative 8. And the way the units would cancel, that would tell us a force of newtons. Now, an interesting other calculation might be actually then to compare that to the gravitational force between these two. So I almost want to do this for my own curiosity. What would be the gravitational force present? Well, if you remember, Newton's universal gravitation is big G, m, r squared. And you should instantly notice that these two equations are relatively similar to each other in how they're constructed. Big G is Newton's gravitational constant, 6.67 times 10 to the negative 11. But anyway, if you were really curious in this, what you would probably try and do is go through and calculate big G times the mass of a proton, which is 1.67 times 10 to the negative 27, times the mass of the electron, 9.11 times 10 to the negative 31 kilograms, divided by that same radius square. It'd be interesting to try and compare the value of the electrostatic force to the gravitational force, but I'm not going to try and throw that in at this time. So we've got a very basic kind of understanding of how this works. The problems with these are actually typically very easy. So what they will do is, a good standard problem would be, let's say you're given 3 charged particles. And you may even be given 4 charged particles. And so they might call them they'll say Q1, Q2, Q3 or something. But usually what they'll end up doing is coming back and they'll throw at you like a value. So let's say that this Q1 has a charge of 2 nanocoulombs, and let's say that charge 3 has a charge of 4 nanocoulombs, and then let's say that this one over here is negative 2 nanocoulombs. And because I'm a bit lazy in my calculations, let's just throw an idea in here. Let's give some separation here. Let's make this a traditional, let's go with a 3, 4, 5 triangle, which means I'm definitely not to scale at this point. But anyway, so what we need to do first is this. Which direction would the forces, how would the forces look like? In other words, on each one of these, how would the forces lay out? Well, if we take a look, this particle and this particle, what's going to be true about those? They're actually going to be attracted to each other. So we would have, going this way, a force of, I'm going to write negative 2, 4. And then, oh, wait a minute, look at this. So here we'd actually have between these two a force of 2, negative 2. I've actually just kind of run out of energy here.